Carbon is a widespread and versatile chemical element. Being an essential and quite active constituent of all natural materials, carbon shows a great variety of forms and is essential to all living processes. Carbon is fundamental in plant photosynthesis. Human beings are made up of 18% carbon. Also, in its pure form, carbon has many faces, such as graphite and diamond. These two materials differ merely in their crystalline structure. In recent years, additional forms of pure carbon have been discovered: fullerenes and nanotubes. Carbon nanotubes are cylindrical molecules of carbon only a few billionths of a meter in size. We are now in the city of Dresden, a well-known symbol of culture and history, and currently experiencing a feverish high-tech boom. Here, at the Institute for Solid-State and Materials Research, scientists and engineers are working on the development and optimization of carbon nanotubes. Initial ingredients are gas and liquid compounds of carbon and hydrogen, so-called hydrocarbons. Nanotubes develop when hydrocarbons are exposed to temperatures of more than 1000 degrees Celsius. But the type and quality of the resulting carbon nanotubes depends to a large extent on the parameters of the production process. The resulting black soot contains countless carbon nanotubes, each of them made of a single layer of carbon atoms. Therefore, they are called single-walled carbon nanotubes. Appearances can be deceiving. What here looks like worthless smut is in reality a network of interwoven carbon nanotubes, each of which is formed by several layers of carbon atoms. Scientists call them multi-walled carbon nanotubes. The extracted substance is still very impure. Therefore, it has to be exposed to a cleaning procedure involving a hydrochloric acid bath, centrifugation, special filters, and drying. It's a painstaking process before the longed-for carbon nanotubes are available in pure quality. But the yield is small. Only 1/10 of the material originally produced in the reactor remains at the end of the complicated procedure. For further investigations, the teeny tubes have to be sliced. No pair of scissors, however small, are able to perform this task. The tool scientists use for this purpose is ultrasound. Similar to a sharp razor, a vibrating titanium finger slits the nanotubes. Single carbon nanotubes can be visualized in the transmission electron microscope using high-energy electron beams. Because of the high surface tension, the carbon nanotubes tend to array in bundles. This cross-section nicely reveals the hollow structure of the nanotubes. Demand for these novel high-tech tubes has increased by leaps and bounds. Their excellent mechanical and electronic properties show much promise in various applications. For example, in novel flat screens where carbon nanotubes can serve as electron sources. On a conducting substrate, physicists nurture a forest comprising millions of aligned nanotubes. If a voltage is applied between the substrate and an opposite electrode, electrons are squirted from the tips of the nanotubes. Electrons impinging onto the opposite screen will result in colored lighting. Who doesn't dream of filling their car up with cheap hydrogen rather than paying excessive amounts for petrol and diesel? In the future, carbon nanotubes might be an integral part of hydrogen-driven cars. Scientists were very excited when early experiments suggested that carbon nanotubes might have a huge storage capacity for hydrogen. Since then, these expectations have proved to be exaggerated, although a storage capacity in the range of 5 to 10 weight% would still be interesting enough to tailor the carbon nanotubes for this purpose. The microelectronic industry is also betting on the novel wonder tube. Depending on the structure, carbon nanotubes can be either metallic or semiconducting. If tiny electrodes were successfully attached to the nanotubes, one could change their electronic properties and switch the electric current just like a transistor, thus opening up new vistas for electronics on the nanoscale. New techniques must be developed to cope with miniaturization tendencies at the atomic level. The path to the future is being blazed today at many research institutions around the world, including the Institute for Solid State and Materials Research in Dresden.